Alright, so example 8 here. We're going to evaluate this definite integral. Okay, so let's just start there. Add 1 to the power, divide by the new power, 1/3 t cubed plus 1/2 t squared plus t, and we're going to evaluate that from 3 to x. So big F of x equals, now the first one's really simple because you're just going to be replacing the t with an x. Great, okay, minus, and I'll group these, why not? This would be what, 9 plus 9/2 plus 3? I'm not going to expand that out right now because I saw that we want to find the derivative. So big F prime of x equals, let's see, that would be x squared plus x plus 1, and the constant part would just disappear. So what do you notice? Have you seen anything like that? It looks remarkably like that. Okay, so that's exactly right. They are very close, except for one's t, one is x. All right, and that's because our derivatives, that implies, that division bar implies division, right? And if we do an integral, say f of x dx, right here, that implies multiplication. These are just inverse operations. They kind of undo each other. So if we take an integral and we take a derivative, then there's this really easy relationship. All right, and we'll see that in the FTOC part 2. But this is just a special case. We're not ready for the whole thing yet. So if f is a continuous function on a closed interval, then big F is defined by the integral of this. And if that is continuous and differentiable, okay, and this is just saying that the derivative of this equals f of x. We can also say this. This is our big deal. Looks really scary, but watch in practice, it's pretty simple. All right, so the hard way would be to integrate that and then take the derivative. The easy way would just be to replace, since we're taking the derivative and we're integrating, we're going to end up with the secant of x. That's it. All right, this next part, we're taking the integral, okay, with a constant 2x and the derivative. So if we do that, we're going to get the cube root of x cubed, the square root of x cubed, times sine of x, the end. All right, and then the last one. Ooh, this one looks scary. Same idea. You're taking the integral from a constant to an x and the derivative of that. So we're just getting e to the x times the square root of x plus x squared all over ln x. The end. All right. If you are just integrating from a constant to an x, this is this most simplest form. This is everything that you can do. Now, of course, that's too easy. So we have to step it up a little. And look at this. What does that look like? What does that look like? Oh, chain rule. All right, we're bringing it back. So when those bounds are not a constant, you have a little bit more work to do. All right, and we'll see it. Hopefully, you'll see it a little bit with this first example. So this is the fundamental theorem of calculus, part 2, and so we're going to evaluate it this way. What you do is you take your function secant squared. Instead of writing t, though, we're going to put in 2x cubed, our top bound. But then you have to multiply it by the derivative of that top bound, which would be 2x. Okay, that's what this is saying. You put your top bound inside of your function, and then you multiply by the derivative of that top bound. Okay, minus, now you take the lower bound, plug it into your function, and you multiply by the derivative of your lower bound, which is just 0. So it turns out this will just be secant squared of 2x cubed times 6x. And it says verify by doing the long way. So I'm going to do that on this one, probably not on the other one, just for sake of time. All right, let's change the color. We're going to do this the long way. We're going to take the antiderivative of secant squared, which will just be what? Tangent of t evaluated from 2x cubed to 1. There we go. So we're going to eventually take the derivative of tangent of 2x cubed minus tangent of 1. All right, so if I take the derivative of this, we get secant squared, secant squared of our inside using the chain rule times the derivative of our inside. Okay, and the derivative of tangent of 1, which is a constant, is just 0. So we end up with the same thing. It's just we found a shortcut to it. All right, so let's try to apply that shortcut again. Let's go back here, okay? So we just plug in the top one, 7 squared plus 5 times 7. That's a 7 there. Not sure what happened. Okay. Times the derivative of our top, which is 0. Okay, minus, plug this in, e to the x squared, or e to the 2x, plus 5 e to the x times the derivative of that bound, which is just e to the x. So in this case, our function is let's put that negative out there, e to the x times e to the 2x plus 5e to the x. And if you want to distribute that out, negative e to the 3x minus 5e to the x, 2x. Sorry about that. All right. So there we go. And this one I can show you using the long way. I just don't want to waste time in the video, so I can show you in class if you'd like to see it. All right. So now we have this huge idea here. All right. So now we can fully apply this fundamental theorem of calculus. Here we go. So we'll do it one more time. This time we get f prime of x equals the derivative of an integral, which we can use now. So we're going to plug in ln of 3 to the x, and we're going to multiply it by the derivative of 3 to the x, which is 3 to the x times ln of 3, minus ln of 2 plus sine of 2x, times the derivative of that inside, which would be cosine of 2x, times 2. And that comes from the inside part of the cosine function. There you go. Big old theorem. Okay, the most important theorem in calculus, the fundamental theorem of calculus, which many other things are based off of. All right. So changing gears here, the mean value theorem for integrals. Now wait, what was the mean value theorem for derivatives? I'm sure that's the first thought that comes to your mind. That was if it's continuous and differentiable on a closed, continuous on a closed interval, differential on an open, then there was some point where the slope of the tangent line matched the slope of the secant line. Right, and as a picture, okay, if you have this function, and here's your endpoints, there you go, somewhere in the middle, your slopes are going to be equal, and it might be right there. Now, this one's a little bit different. The mean value theorem for integrals. So if f is a continuous on a closed interval, again, then there exists a number c, x equals c, in the closed interval. So before with derivatives, it had to be on that open interval from a to b. It couldn't be an endpoint. But now, with this, it can be an endpoint. All right, such that this integral, the accumulation, okay, the area, under the curve would be equal to f of c, some y value, times b minus a. All right, now this looks kind of confusing, and it's not too bad. So what it's saying is there's some particular height, f of c, right here, such that when you find, let's say this, we have the area under this curve, right? This would be something, we don't know what it is exactly because we don't have a function, but for some y value, okay, that gives us a height that when we do this width times that height, this area, in fact, matches the exact area under the curve. All right, and so again, I'll try to break it down a little bit more. So somewhere there exists a particular height such that the area of the rectangle is the same as the area under the curve. Okay, that height, that f of c, just has a different name. It's called the average value. All right, so Another way, if I wanted to solve this equation right here for f of c, that average value, then I would just divide by b minus a. So you can write it as divided by b minus a, or you could pull it out front, do 1 over b minus a. And I'm sure you guys are going to have a little bit of confusion, but maybe, you know, an example could help clear that up. So, so a good example might be like, let's say we call that temperature over time, right? So the temperature changes throughout the day. So it might be something like this. Maybe it got colder, the big winter storms coming in, right? Throughout a whole day. So we'll say 0 to 24. Well, if you wanted to find that average temperature, you could start by maybe taking time, the temperature every hour, and you'd have like these finite data points. Okay, but that's not going to be too helpful because it could change. It might have dropped a lot. It would be okay to get even more accurate, right? And sorry, times in hours here. To get more accurate, you could take it every half an hour, which wouldn't be a fun day, but you could do it. And you could get even more accurate by taking every minute, but you're still not going to get that exact average value. Okay, instead, if there was a way you could model it by a function, then you could find that average value, that average temperature, by doing this kind of function. Okay, you could do 24 minus 0 times the area, okay, and that'll give us that average temperature. That'll give us at some point, and then, you know, maybe the average temperature would be, I don't know, say that's like 50 degrees. That's really warm for right now, but maybe, I mean, you don't know. So maybe, you know, you could find out, oh, it hit 50 3 times that day. All right, so we'll do examples, and maybe it'll help clear it up. But I just wanted to give you that introduction into what this mean value theorem is. Okay, and I don't want to just leave you with all of these words. We'll try a quick example. All right, so we're trying to find the average temperature of this town in Texas that we've heard of many times and probably have never been to. Okay, so here we go. The average temperature during a 12-hour period from 9 to 9. And t is in hours after 9. So we're going from t equals 0 to t equals 12. Find the average temperature. So using that idea, okay, that you should label what you're talking about. Average temperature is equal to, so you're thinking like the area of, I'm trying to explain it in the best way possible. I don't care if you use this formula or this one. So it's like this b minus a, that's the width. That's the time that we're talking about, all right? So it's 1 over 12 minus 0 times the integral, or the accumulation, okay, the temperature, the accumulation of temperature from 0 to 12. And because it's labeled already, I'm just going to go ahead and write the function in. If it's labeled, and if you have a calculator, you're probably going to put that right into your calculator, especially if there's more than one part, okay? And so just type it into your calculator, and you're going to get either 58.912, or it depends if you round it, okay, 913. Either way, degrees Fahrenheit. You should always label when you have word problems. So there you go. The average temperature in this problem would be 58.912. All right. Now, this is a neat thing that you can do with a calculator. Okay, you can even do it even if you're scared to use your calculator. We find the values of T at which the MVT guarantees the temperature was the average temperature. So we're trying to figure out, where does the function equal that value? All right, and so where does the function equal that value? And it's 58.912, but it wasn't exactly that. Okay, you rounded. So you can store that into your calculator as some letter. Why not A? Okay, it doesn't matter. And you can solve on your calculator. You can ask, where does this function, and you probably have it in y1, so you might type like y1 of x equals A with respect to x. You could solve it. Okay, solve. That's how you would type it into your calculator. And if you want a decimal approximation, okay, it'll give you that, and it'll give you two values. You'd see it'd be about 9.363 or 9.364 hours. All right, so there you go. That's exactly where. So if you wanted to get a graph of this, that's a sine function moved up 50 units. Um, the periods changed a little bit, so I don't know, it might look something like this, and you could get a better graph. All right, and so the average temperature is about 58. So like this, right? So somewhere between 0 and 12, the area of this rectangle matches the area under the curve. Okay, and it looks like this, that's what we figured out by this integral equation in blue. And there are 2 times when the temperature reached that. And those are the, oh, I only wrote 1. Huh. Okay, well there are 2 times. One is about 9 point something, and the other one is about 2.636 hours. Okay, and that would be right about there. So there you go. Have a great day.